The world around us is full of dangers. Sometimes we are so busy with our own affairs that we simply forget about it. But as soon as something terrible happens, we immediately realize how utterly defenseless we are. About 66 million years ago, according to the Alvarez hypothesis, an asteroid crashed into our planet, creating a shock wave that killed many dinosaurs. So much dust was thrown into the air that it was as dark during the day as it was at night. Due to the lack of light, the climate on Earth became very cold, which was the cause of the complete extinction of ancient reptiles. In many disaster movies, we are shown scenarios where a space object is heading towards our planet, which is also capable of destroying all life. But what is the reality? Our space journey offers you to find out which asteroids are currently hurtling towards Earth at breakneck speed. What are the dangers of such encounters and how can we avoid them? Let's find out. What has fallen on Earth before? In terms of terminology, a collision of a large meteorite, asteroid, comet, or other celestial body with Earth is called an impact event. According to scientists' estimates, a collision with a celestial body of about 10 kilometers in size that is capable of destroying human civilization can occur approximately once every 100 million years. Such collisions have not occurred during the entire history of modern humans, about 100,000 years, said Igor Bakaras, head of the Information and Analytical Center for Ensuring the Safety of Space Activities in the Near-Earth Space of the Main Scientific Institute of Roscosmos, in an interview with RIA Novosti in 2019. Of course, one would like to believe that such an event will never happen. But let's remember, have there been any precedents for such dangers before? The last such incident that could have resulted in mass casualties was the fall of the Tunguska meteorite in 1908 in a remote corner of Siberia. It is believed to have exploded at an altitude of approximately 10 kilometers. For several nights after the event, there was a glow in the sky and glowing clouds. The forest was flattened over an area of 2,000 square kilometers. Research expeditions did not reach the site until 15 years later, and while significant meteorite fragments were not found, they did discover microscopic beads that indicated a cosmic origin of the material. Such collisions occur every few centuries, but there are exceptions. Another event, known as the Brazilian Tunguska, occurred 22 years after the described incident. In August of 1930, during the annual maximum of the Perseid meteor shower, in the early morning hours, the sun turned red, ash fell, and there was a loud roar. The explosions were audible up to 250 kilometers away. Despite being compared to the Tunguska meteorite, the explosion's power was incomparably smaller, about 10 to 15 times less. Decades later, a region with a diameter of 1.5 kilometers in a fallen forest was discovered from a satellite. And relatively recently, we witnessed a repetition of this terrible scenario on a smaller scale. In 2013, a meteorite exploded over Chelyabinsk at an altitude of 30 kilometers. Windows were shattered, and 1,400 people were injured. The explosion's power was equivalent to about 500 kilotons, roughly 30 times the power of the atomic bomb dropped by the United States on Hiroshima. Again, the explosion occurred quite high above the ground, which prevented serious damage. And it turns out that such collisions happen much more often, about 3 times a year. Most of them happen over the ocean or in remote corners of the planet, so we usually don't notice them. One of the latest large meteorites that fell on Earth was the Kamchatka meteorite. It exploded over the Bering Sea in December 2018. The explosion was detected by NASA satellites hundreds of kilometers from the Kamchatka coast and occurred at a height of 26 kilometers above the sea. The most dangerous asteroids have been identified through years of research. It has been found that a collision between Earth and dangerous cosmic objects does not occur when they are moving along the same trajectory, but at different times. Researchers have identified the following most dangerous asteroids whose trajectories intersect with Earth: 1950 Bennu, Apophis, 2009 FD, and 2010 AU 118. Astronomers rank asteroids on the Palermo scale, a special scale of danger. The most dangerous asteroid until 2021 was considered to be Apophis, which has a diameter of about 325 meters. Its average approach to Earth is approximately 31,000 kilometers from the planet's surface, about 1/10 of the distance from Earth to the Moon. Recently, scientists were able to determine that the asteroid is not dangerous for the next 100 years and it is likely to fly by. However, the small near-Earth asteroid 1950 from the Apollo group is noteworthy primarily for having the highest index on the Palermo scale of hazard. The maximum approach to Earth is expected in 2032, and a possible collision may occur in 2880. In this case, if human civilization still exists in 800 years, catastrophic consequences await it. Our descendants must be prepared for a global climate change and the destruction of a significant part of the biosphere if they do not learn to prevent such events. Bennu is the next most dangerous asteroid for our planet. In 2135, it will be only 300,000 kilometers away from Earth, even closer than the Moon. The possible date of impact ranges between 2175 and 2199, and during this period, it will approach the Earth 78 times at a close distance. The asteroid's average diameter is over 510 meters, and its mass ranges from 60 to 78 million tons. The impact of this asteroid on Earth would be equivalent to the explosion of a bomb with a power of 1150 megatons in TNT equivalent. For comparison, the Tsar Bomb, the most powerful explosive device ever tested by humans on Earth, had an explosion power of about 58 megatons in TNT equivalent. This asteroid is also interesting because it is the target of the OSIRIS-REx space probe mission launched by NASA in September 2016. The spacecraft is expected to return samples to Earth in 2023. The next most dangerous asteroid is 2009 FD, which is a binary, meaning it is a system of two celestial bodies gravitationally bound to each other. A binary asteroid consisting of two gravitationally bound bodies that rotate around a common center of mass, much like the components of a double star. The first component has a diameter of 120 to 180 meters, and the second has a diameter of 60 to 120 meters. The mass of 2009 FD is about 3.2 million tons. Scientists believe that binary asteroids have already fallen on Earth, as evidenced by some impact craters, such as the Clearwater Double Crater in Quebec, Canada. 2009 FD passed by Earth on October 29, 2015, and November 3, 2020. The most dangerous period for Earth is when it will be closest to the planet, which is in the year 2198. Finally, there is asteroid 2010 AU 118, with a calculated diameter of 1.9 kilometers. This is the largest object listed in the Sentry Risk Table, a collision monitoring system created by NASA. Its specialists constantly scan the latest observations of asteroids and determine the probability of their collision with Earth. The most interesting thing is that as a result of software updates, 2010 AU-118 was repeatedly removed and then added back to this list. It takes 754 days for one orbit around the Sun. The number of potentially hazardous close approaches from 2020 to 2112 is 38. Well, in 2020, it didn't collide with Earth, which is good news. Hopefully, it will continue like this in the future. How do we deal with this? However, the question is not whether a collision will occur, but when it will occur. Governments around the world take this problem seriously and are taking initial steps to avoid a dangerous collision. The first thing humanity needs to do is to build telescopes and observatories. A large telescope can see a cosmic object long before it approaches Earth's orbit. So scientists from the University of Hawaii's Institute for Astronomy, who are searching for hazardous asteroids, will now be observing the sky in the southern hemisphere. Their capabilities were expanded with the help of 2 additional instruments. The Asteroid Terrestrial Impact Last Alert System project, funded by NASA, aims to track small asteroids with diameters in the tens of meters. One of the new telescopes is located at the Sutherland Observatory in South Africa, while the other is at the El Sos Observatory in Chile. Such a placement of instruments not only allows for a view of the entire sky, but also enables the tracking of hazardous asteroids 24 hours a day from observation points in different time zones. On January 22, 2022, the South African Observatory reported the discovery of a 100-meter asteroid named 2022 BK, which fortunately will pass by our planet. The launch of the first Russian specialized satellite for space debris control is expected in 2027. These devices will be part of the Milky Way system, according to Alexander Blashenko, Executive Director of Roscosmos for Perspective Programs and Science, in an interview with TASS. The U.S. National Aeronautics and Space Administration (NASA) has also established a Planetary Defense Coordination Office as the single responsible entity for asteroid observation. Participants in the European-American project for the study of asteroids (AIDA Asteroid Impact and Deflection Assessment) have even chosen a target for their mission. A pair of automatic stations will be sent to the Didymos double asteroid, according to the European Space Agency. The Didymos asteroid consists of a main body with a diameter of 800 meters and a satellite measuring 150 meters, which orbit each other at a distance of about 1.1 kilometers. The AIDA project involves sending 2 small spacecraft to the asteroid. One of them will crash into the smaller asteroid at a speed of about 6.5 kilometers per second, while the other will observe. Scientists hope to detect changes in the orbital movement of the 2 bodies caused by the impact. Scientists emphasize that the goal of the project is not to develop the technology for intercepting dangerous asteroids, but this is a first step towards such technology. In 2014, the Japanese Space Agency launched the Hayabusa spacecraft to orbit the asteroid Ryugu, and 2 years later, the U.S. launched the OSIRIS-REx interplanetary spacecraft to orbit Bennu 1999 RQ-36, which landed on the asteroid in 2019. Overall, the search for potentially hazardous asteroids is being conducted by more than a dozen projects, including ground-based and orbital spacecraft. A large number of observers and their communication in a unified network allow for impressive results. In March 2022, the fifth asteroid was detected before it fell to Earth. On March 2011, Christian Charnetsky, a geography teacher and asteroid hunter, noticed a new moving near-Earth object on his images. He reported the find to the Minor Planet Center. At first, the probability of a collision was estimated at 1%, but a few hours later, the Meerkat system of the European Space Agency raised the alarm. More accurately calculated parameters of the object's orbit indicated an inevitable collision. Despite the difficulties of finding the object, which was already closer than 50,000 kilometers to Earth and was rapidly moving across the sky, additional observers were brought in. It turned out to be a meteoroid with a diameter of about 1 meter that was expected to enter the atmosphere around Iceland. And so it happened. The flash was recorded by cameras in Norway, and the fall was confirmed by a network of infrasound detectors. But telescopes alone are not enough. It is necessary to mobilize forces to create a powerful technological invention, such as a laser gun or a rocket launcher that will be loaded with nuclear bombs, turning the space object into dust. At the current stage of development, various methods of combating asteroids are being considered. NASA has concluded that nuclear implosion can be used to deflect near-Earth objects with a diameter of 100 to 500 meters if they are detected 2 years before they fall to Earth, and objects of larger sizes if they are detected 5 years before. Another method is to send a huge object, such as a spacecraft or even another near-Earth object, as a ram. Or, for example, an asteroid gravitational tow. Another alternative to explosions is the slow shifting of the asteroid over a certain period of time. An automatic system located on an asteroid releases the material it is made of into space, causing it to slowly shift and lose mass. An electromagnetic catapult is proposed to work as a low specific impulse system, which uses a lot of fuel but little energy. Another possible solution is to place the electromagnetic catapult on the Moon and aim it at a near-Earth object. Rocket engines installed on the asteroid might also be a logical solution. Ordinary rocket engines are installed on the near-Earth object to create a constant deviation of the asteroid's trajectory. Whatever method is chosen, its effectiveness will be crucial for the survival of humanity. In conclusion, if you hear in the media that a scary asteroid is about to fall, the best thing to do is to visit the website of the NASA Near-Earth Object Program or the ESA Space Situational Awareness Program to search for the mentioned asteroid. While Roscosmos does not currently provide such a convenient table, they have already started commenting on emerging news by checking the trajectory of the object themselves. Usually, this simple action is very reassuring. The asteroid may be small, the potential collision date might be in the middle of the millennium, or the probability of collision is ridiculously small, or all of the above. In general, although a meteorite the size of the Chelyabinsk meteorite can still come suddenly, most large asteroids have already been found, and humanity is actively and successfully working to catalog potentially hazardous objects.
Checking out traffic this morning along the Keighley Gardner, Guy Valentine.
It's a bit of a battle for drivers without cover. I'm talking if you don't have any shade, you're fighting some pretty bright sunshine.
And also caution on Highway 7 going east of Keighley.
And northbound Don Valley Parkway on the ramp to eastbound 401, we've got a disabled vehicle.
June the 14th, 2002. It was just another busy workday with all the usual hustle and congestion. With all the close calls and near misses that people all over the world have come to accept as the normal level of risk in everyday life. But on that day, high overhead and behind the sun, what no one saw coming, what no telescope on Earth was able to see against the blinding light, was an asteroid big enough to destroy an entire city. From behind the sun, asteroid 2002 MN came hurtling towards Earth, faster than a speeding bullet. It shot past, less than a third the distance to the moon, and nobody saw it, until 3 days later, when the rock emerged from Earth's shadow into the night sky, going away.
It looks like the Earth just dodged a bullet. Actually, it was an asteroid. Scientists say it blew by last week at a distance they describe as a close shave.
The airline industry would call this a near miss. Scientists who study asteroids and comets called it a problem.
The threat of asteroid impacts on the Earth is very real. We know that throughout history this has happened. The craters we see on the moon are examples of the kind of impact history that the Earth has had. But it also happens very rarely. So it's a very unusual kind of hazard. It's a hazard in which the risk in any one year is very low, but it does happen, and if it really did come about on our watch, it could end civilization.
These cosmic bullets originate on the far side of Mars, in the main asteroid belt, where a bracelet of celestial debris circles the sun. Millions of rocky fragments, building blocks of a planet that never quite came together when the solar system was formed. What's often depicted as a busy cosmic junkyard is actually more like a big empty speedway. The rocks are far apart and moving very fast, ranging in size from pebbles to boulders to rocks the size of Mount Everest. Occasionally, the tug of Jupiter's enormous gravity drags an asteroid off course, causing it to crash into another asteroid. Some veer away into new orbits that cross the paths of Mars, Earth, Venus or Mercury. Another ring of debris called the Oort cloud is the source of most comets, which are big, rocky ice balls that orbit the sun and cross the paths of the inner planets. All the inner planets and our moon bear the scars of numerous asteroid and comet impacts.
We do get hit all the time by pieces of debris from asteroids and comets. In fact, 40,000 tons of cosmic debris plummets into the atmosphere every year. We see them every night as shooting stars. They don't hit the Earth very often, but when they do, clearly it isn't just going to be a matter of a shooting star seen in the sky. So it is inevitable. It's only a matter of time before the next big one hits us.
Even small rocks can make a big impression. In 1908, about 2,000 square kilometers of Siberian forest were instantly flattened as an asteroid exploded near the Tunguska River. The impact site was so remote, researchers had to mount a wilderness expedition just to find the place. When they arrived, there was no crater. Paintings, based on eyewitness accounts, described a fireball. A horrendous explosion in the sky.
Didn't actually come crashing down to the ground. It exploded maybe 5 to 10 kilometers up in the atmosphere, and that made a big blast wave in the atmosphere, and that is what did the damage.
All this was caused by a relatively small asteroid, somewhere between 50 and 100 meters across. Roughly the same size as asteroid 2002 MN, the one we couldn't see coming. Tunguska's 2,000 square kilometer blast wave would have leveled London. But as bleak as the thought of cosmic collision may be, there is at least a glimmer of hope.
One of the special things about the asteroid impact problem is that unlike the weather or earthquakes or other natural hazards, we, at least in principle, we could do something about it.
And when we know one's coming for us, our claim is that the technology is available today to stop it.
On the Earth, we've got active geology, we've got volcanoes, we've got earthquakes, we've got continental drift, we've got rain, we've got wind, we've got storms, we've got snow. All of those things erode away craters, and that, in some ways, actually fools us into thinking that indeed the Earth doesn't get hit as often as it actually does.
Counting craters on the Moon and then estimating how often the Earth gets hit can be a pretty sobering exercise. One scientist who made that kind of calculation was astronomer Ernst Opic, who published his impact estimate back in 1951. The general public, however, paid little attention to the science or the implications. But one individual who did take the issue to heart was Lembit Opic, the astronomer's grandson, who got himself elected to Parliament.
My grandfather is the reason why I carried on in politics, what he initiated in science. In essence, he was a pioneer. He saw the danger of asteroid and cometary impacts with the Earth, and he had the courage to speak up about them. And he did that at a time when it wasn't really taken seriously, in the 1950s and 1960s.
After years of pushing and prodding, Lembit Opic convinced the British government to commission a comprehensive scientific study of the asteroid and comet threat. The expert conclusion was, the threat is indeed real.
Now, the government has set up a task force to examine the risk of an asteroid hitting the Earth.
Still, skeptical politicians might want to get on the bus and take a trip to the Natural History Museum. Ask any schoolchild who's been there recently, and you'll hear a fascinating and truly scary tale about what happened to the dinosaurs.
The dinosaurs were alive here. They were dead when this sediment was deposited, and this layer is one of the most unique layers in Earth history.
In 1980, the discovery of iridium beside a layer of clay which marked the end of the age of dinosaurs led Lewis and Walter Alvarez to publish a theory that a huge asteroid or comet had hit the Earth 65 million years ago and wiped out the dinosaurs. But for this concept to be confirmed, there had to be a crater. There may be tons of dinosaur bones in these dry canyons, but where on Earth was the big crater? Just the kind of mystery a budding young scientist would love to solve.
When I went back to...
Off the coast of Mexico's Yucatan Peninsula, Dr. Alan Hildebrand investigated a huge gravity anomaly discovered by oil drillers back in the 1950s. Put that together with a semicircular magnetic anomaly, and you get a massive crater, 180 kilometers across, near a little village called Chicxulub Pueblo. Most of the crater is underwater now. Erosion and continental drift have covered the visible evidence. But 65 million years ago, this was ground zero.
This object would have fallen through the atmosphere in just a few seconds. It's going through the sky, it would have been brighter than the sun. As soon as it contacts the surface of the shallow sea in Chicxulub, of course, it starts propagating the shock wave down into the planet, and it keeps pushing into the planet, and it only gets stopped maybe about 30 kilometers down. The pressure wave would have traveled around the entire planet in the atmosphere. You could have heard the impact on the other side of the planet. The giant impact fireball rising out of the hole, it would have risen, say, 10,000 kilometers above the surface of the planet. Near the impact site, it would have been so hot, it would have evaporated the clouds and been hot enough to make the forest, even a green forest, begin to burn.
For Alan Hildebrand, finding that crater pretty much clinched the argument. Planet Earth had been all but sterilized by a rock the size of Mount Everest.
3/4 of the species of large animal life went extinct.
We have made the case. We've got the qualitative information and we've got the statistics to show that there is a very serious risk.
If you wanted to save planet Earth from cosmic disaster, where would you find people with all the right stuff to do the job? Well, Houston, Texas might be a good place to start looking. This town has that rarest of breeds, the space cowboy. Houston is home to NASA's Johnson Space Center, where rocket science is a way of life and astronauts learn their trade.
If you could roll me 90 and then go down, I'll come in on my side.
Behind a swimming pool big enough to swallow an apartment block, you'll find a small research lab where the rocket engine of the future is being built and bench tested.
Yeah. Very nice. Question is, how big is the plasma going to go from here to here?
Dr. Franklin Chang Diaz is one of the lead researchers, as well as an astronaut with 7 shuttle missions under his belt.
And in fact, there was a time in one of my flights where we got hit by very tiny micro meteorites, perhaps, or some sort of orbital debris, which made little tiny dents or little craters in the windows of the shuttle.
Well, that tube is welded. Yeah, I did it. We already welded it. Yeah, I did it.
First-hand experience with rocks in space gave birth to a new idea and a dual purpose to Chang Diaz's work here. His rocket engine has been developed for long-distance missions to Mars, or as far away as the icy moons of Jupiter. But it could also be used to push a dangerous asteroid out of harm's way.
I am concerned enough to think that we need to not waste time arguing about it as to whether it's real or not. I think we need to move ahead. If this is a threat which has a very low probability, all it takes is one, and we are history.
But before we can send a spacecraft chasing after a rogue asteroid, we have to know where to look for it. In the American West, if you drive across the desert to the White Sands Missile Range in southern New Mexico, you'll find the most powerful and effective asteroid hunter on Earth. Scientists here have tested everything from rockets to the very first atomic bomb. Today, across the valley floor from the Trinity bomb site, the US Air Force has installed one of the world's most advanced telescopes. This state-of-the-art technology was developed by MIT's Lincoln Laboratory as part of the Star Wars anti-missile defense system. These may not be the world's biggest telescopes, but they clearly are the best when it comes to finding deadly rocks in space. This is LINEAR, the Lincoln Near-Earth Asteroid Research Facility.
On a given night when we scan the sky with this, we'll find perhaps 10 to 12,000 moving objects in the sky. Now, most of those are main belt asteroids and as such don't represent any danger to Earth. But on the other hand, something like half of those will be brand new discoveries, and buried in there will be 1 or 2 near-Earth objects.
Because the Earth rotates, the sky is always moving overhead. To get a clear picture of an asteroid, you have to make the sky stop moving. And you do that with a telescope that can track or follow the stars. This way, you can take time-lapse pictures that isolate the blur of fast-moving asteroids against a crystal-clear sky. It then records these pictures like a TV camera on a computer chip that has 20 times more detail than the picture you're now watching. The linear computer deletes previously known stars and planets, leaving a less cluttered time-lapse sequence of the new discoveries. At the end of each night shift, Linear's thousands of new discoveries are emailed to the International Astronomical Union's Minor Planet Center at Harvard University. A team of only 3 scientists must cope with the avalanche of new sightings, searching for potentially hazardous asteroids or comets. Computers make a rough calculation of an asteroid's orbit, but it's up to Brian Marsden to estimate the level of risk.
They may be reporting 50 or 60,000 observations from one night, and it takes a while to get through that. But so we look first at the fast movers and see if there's anything interesting there. H is equal to sine delta. We do sometimes get close to 70 or 80,000 observations a day, almost 1 per second. There are some days when we effectively have 1 observation per second.
Even with fast computers, Marsden's team can make only a preliminary calculation of each asteroid's orbit. 5 shots in one night cover only a tiny segment of an asteroid's orbital path.
You can't solve for the orbit completely from that, but the fact that you're seeing motion over a half an hour or an hour, something like that, does allow us to get a partial solution for the orbit.
Refining the orbit gets complicated. When 2002 MN shot past, its trajectory was warped by Earth gravity, and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, had to add that to their calculations.
Here's an animation I put together of the asteroid last year, which was discovered after it passed by the Earth.
An elite team of mathematicians and celestial mechanics is now working full-time on a computerized warning system.
Our orbit animation, you can see how when it returns out to the asteroid belt, the close approach to the Earth has changed its orbit, and it's no longer returning to the same place it started.
Because 2002 MN will circle around the Sun and come past us again, the NASA Orbital Mechanics team will have to adjust the calculation in order to know whether it will ever pose a danger to Earth at some point in the future.
So here we've zoomed in on the Earth-Moon system and we're looking down. You can see how close it came to the Earth. It went over the top, and how you can actually even see the bend in the trajectory. So it's a great example of how a close approach to the Earth, or in fact any planet, can be used to, or can change, significantly change in orbit.
To know where an asteroid is likely to be in the future, you need a model of the solar system. Mechanical models that show the relative motions of the Sun and planets have been around since the early 18th century. They're called orreries. What the celestial mechanics at NASA had to do was create a new digital model. One that includes the gravitational attractions of all the planets and the Sun, and all the other forces that can affect where an asteroid might go.
You just compute what forces are acting on this particular asteroid from all the planets and many of the minor planets in the solar system, and then we can actually trace the motion of that object around the solar system for hundreds of years.
For scientists, the acid test of their mathematics came when a strange new comet raced toward Jupiter. A stream of cosmic bullets that would shock and amaze millions here on Earth. In the spring of 1993, the eyes of the world turned almost in unison towards a doomsday rock like no other. From the far side of the solar system, it flew in a death spiral toward the largest planet. Gene Schumacher, his wife Carolyn, and their colleague David Levy had discovered an odd-looking streak of light that turned out to be a fractured comet. 21 large chunks of icy rock and cosmic dust heading towards Jupiter.
We knew we had something very unusual. It was so unusual we were a little unsure just what we were dealing with.
NASA asked Paul Chodas and his team to calculate the orbit and predict whether this new comet would actually hit Jupiter.
And it started off at some 60%, and before long it was 90%, and this was a year before impacts. As the impacts approached, we continued to predict not just the impact probability, which went very high, but where and when the comet fragments would hit the planet. And it was a prediction months in advance. And as we got closer and closer to the impacts, I kept wondering, well, is the math right? Will this actually happen the way it was predicted?
A giant comet is on a collision course with Jupiter.
Everybody on Earth who was paying any attention wanted to see if the comet would actually hit Jupiter.
We have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
NASA's Hubble Space Telescope set its sights on the planet, and the pictures of what happened next were truly stunning.
Right there! Get it! Wait.
And then the impacts occurred. We were within minutes of getting the right answer on the time of impact, and the location of impact turned out to be just right.
Over the next week, 20 more fragments of the comet crashed into Jupiter, some leaving scars as large as the Earth.
Bang on its cosmic schedule, the comet's first impact was recorded by NASA within the last hour.
When fragment G slammed into Jupiter, releasing an amount of energy equivalent to about 6 million megatons of TNT.
In the wake of SL9, a group of concerned scientists gathered in Italy for a brainstorming session.
Hello.
They created a brand new international organization called the Space Guard Foundation.
Okay, I'm going to join.
To promote the discovery and study of near-Earth objects.
Some people imagine that there are lots of astronomers out there scanning the sky looking for incoming comets and asteroids, and that, of course, is not true. In fact, until recently, there was hardly anyone out there looking.
It's going to glow for about a half an hour and set everything on fire around you.
But whose job is it to defend planet Earth? Weapons scientists from the United States and Russia had already held a series of meetings and came up with their own ideas about how to deal with the impact threat.
Blow off some material, you get a reaction in this perpendicular direction.
The military establishment under Star Wars had created a whole lot of devices, or at least concepts, for weapons in space and devices in space. And in the early 90s, when the Star Wars program was looking a little bit iffy, I think there was some motivation for them to try to apply their technology to this newly discovered hazard from asteroids and comets.
The military approach to the problem proved to be controversial. The notion of sending nuclear weapons into space generated an immediate backlash.
Edward Teller was proposing that we blow up an asteroid to show that we could protect the Earth, and I thought that was a pretty crazy idea. Blowing up an asteroid with a big bomb has a lot of problems associated with it, violating treaties, taking a single asteroid and making a swarm of smaller asteroids. It seemed like it was more of an interest in bombs than it was a serious interest in defending the planet. For NASA, on the other hand, NASA obviously is the natural agency to discover the threat and the objects, but they say no, planetary defense, that's a military obligation and not an obligation of NASA.
Not NASA, not the military, Just when it seemed planetary defense was nobody's job, a tiny speck in the sky would set off doomsday alarms around the world. On a winter's night, the 6th of December 1997, a dim streak of light moving through the constellation Cancer was captured by a telescope in the Arizona desert. Big enough to destroy civilization as we know it, asteroid 1997 XF11 seemed to be heading towards Earth. The initial sighting by the Kitt Peak Observatory in Tucson, Arizona, was relayed to the Minor Planet Center at Harvard University in Cambridge, where a computer made the first rough calculation of the orbit. They were pretty sure it would miss the Earth on this pass, but it would be coming round again, and it looked like there could be a problem in 30 years.
There were indications of close approach to the Earth in 2028. That was about 45,000 kilometers, which really was rather close.
With only a handful of sightings, the orbit calculation remained very rough. It was hard to tell where this rock was going. So Brian Marsden posted a bulletin asking astronomers around the world for more observations before the rock became too faint to see.
I was saying, hey, get your big telescopes onto this. On the one hand, we're only going to be able to observe it for another month or so. We want to improve the orbit calculation and find out exactly how close it is coming.
But one line in the bulletin said that the chance of a collision was small, but it was not entirely out of the question. Within hours of the website posting, reporters discovered XF11, and doomsday headlines screamed around the world. Because the close approach in 2028 would put the asteroid nearest to Europe, London newspapers focused on the exact moment life on Earth might possibly end.
Pictures of it on the internet show it as a tiny moving blob. Scientists have calculated its path in the year 2028.
Watch very carefully. September, October the 28th, the two coalesce.
But at NASA's Jet Propulsion Laboratory in California, the orbital dynamics team thought there must be some mistake.
Asteroid's orbit was affected by it. To my great surprise, when we ran our software, it said that the probability of impact of this particular asteroid in 30 years was essentially zero.
As it turned out, the end-of-the-world asteroid would miss the Earth. That big rock in space posed no threat after all. A frantic hunt through the archives at NASA had turned up photographs of XF11 taken 8 years earlier.
And as soon as those were placed into the orbit determination process, they confirmed the fact that there was no chance that it could hit the Earth in 30 years.
The public at large was not understanding uncertainty in this. They wanted an immediate answer. Is it going to hit us or not?
But people were paying attention. One side effect of the false alarm was that public and political awareness of the threat had been raised. 2 months after XF11, new hearings were held in Washington, and NASA was told to speed up the science of asteroid detection. Finally, it seemed, there was a political will to do something. Congress gave NASA a 10-year deadline to search the skies and get a fix on the largest of the doomsday rocks. They called it the Space Guard Survey. While astronomers geared up to search the skies, Hollywood was going into overdrive.
I would go to every dinner party and I would say, are you aware what would happen if a comet was actually on a collision course with the Earth?
Oscar-winning screenwriter Bruce Joel Rubin was hard at work on the remake of a sci-fi classic. The new film, called Deep Impact, would be a Steven Spielberg production.
An army of scientists work desperately to build this giant rocket, this modern Noah's Ark, to carry a few picked survivors of our doomed civilization.
I think the thing that was hardest for me was the realization that people would have to be chosen to survive.
Let's take the ship away from them! Come on!
Probably a very, very small percentage of human beings would be left on the Earth able to survive something of the intensity of the comet that hit and destroyed the dinosaurs. So I felt making this movie is not just a mission to tell a good story, it's to change minds. It's to let people go, this is something real. This can happen to us. This movie is a wake-up call. It's not just a Hollywood movie, it is pointing at you.
As Hollywood released Deep Impact, telling the world in no uncertain terms that cosmic collisions were no longer just a cosmic joke, real-life professional asteroid hunters were making movies of their own. But instead of using cameras, they worked with delayed Doppler radar. Take the same technology behind a police radar system, jump the power to 400,000 watts, and you've got NASA's Deep Space Network with huge multi-dish systems like the Goldstone tracking station in California's Mojave Desert.
This is the main room of the pedestal of DSS-14.
The first time radar astronomer Stephen Ostro bounced a signal off a rock in space, a wobbling blot of pixelated data bounced back. What looks like digital gibberish spoke volumes to Steve Ostro.
Radar really does three things at once. One, it works at long wavelengths, so you're sensitive to structure on large scales and metal concentration. The other is you can make pictures. And you can't do this from the ground in any other way. You make pictures of objects, and then we take a sequence of pictures, and we go through a computational process to produce the 3D models. That's the second thing. The third thing is that it makes very precise measurements of distance and speed.
When the 1,000-foot radar dish at Arecibo in Puerto Rico bounced a beam off an asteroid called Castalia, the data was translated into a 3D computer model. The very first radar movie showed how Castalia spins and revealed that it was actually two massive chunks of rock held together by weak gravity. Every time they made the trip to Goldstone for a new radar target, Ostro and his team were like kids reaching into a box of chocolates. They never really knew just what they would find. Asteroid Cleopatra, shaped like a dog bone, was roughly the same size as the state of New Jersey and was made almost entirely of metal. Echoes from asteroid Tutatis produced images of a rocky, cratered surface and a wobbling, tumbling spin.
Every single one of these objects that we've made a shape model of is very different. This is Tutatis.
From a telescopic smudge of light to a 3D shape model, radar gave them physical details and the first clear idea of what asteroids are really like. In the year 2000, the radar movie crew developed a dark and mysterious new image, Asteroid 1950 DA, a big rock that gave everybody a bit of a shock.
Once we got the radar data, we began the normal process of just seeing how far in the future we could predict this thing before the uncertainties in the orbit blur out. And in this case, we could go over 880 years into the future. And what was startling about that case was the impact probability turned out to be non-zero.
Non-zero means there is a chance this rock could hit us. On March the 16th, in the year 2880, 1950 DA will cross the Earth's orbit. Will it hit us? The odds? 1 in 300. If 1950 DA does hit the Earth, the most likely point of impact would be at sea. Of all the big asteroids discovered thus far, this is the most dangerous one we know. Eric Asfaug and Stephen Ward have created a computer model of the impact.
Yeah, it's kind of funny how this started. It was with the movie Deep Impact, and I was getting phone calls. Lots of people were getting phone calls about the movie, whether it was accurate, the big cresting tsunami coming across.
The concept here is that this asteroid, which is about 1 kilometer across, will hit the ocean at 17,000 miles per hour, and it'll blow a hole in the ocean about 19 kilometers across and all the way to the bottom. And so when this huge hole of water gets blown into the ocean, the water will run back in again, and it overshoots and it collapses and overshoots many, many times, and each time it pumps out a wave. So it starts out hundreds of meters high, comes ashore on the coast of North America at about 50, 60 meters. Up toward Canada, Grand Banks, it's about 40 meters, 20 meters here in the coast of South America, and about 15, 20 meters all the way over to Europe. These waves would run inland about 4 kilometers. So pretty much everything within 4 kilometers from the beach would be covered up repeatedly. And so we'd pretty much be wiped away like you're scrubbing the floor. You know? Just scrub like this, and it's pretty much all be carried back out.
In February 2001, a NASA spacecraft called Near Schumacher made the first ever landing on a chunky, pockmarked rock named after the Greek god of love. Asteroid 433 Eros is 33 kilometers long and 13 kilometers wide, one of the largest near-Earth asteroids. The pictures were spectacular. The data will take years to process. Proving that they could land on an asteroid was a major achievement, but in the end, they still don't know much about what's inside. How dense? How tough? How brittle or crumbly is it? What would happen if they gave it a good shove? The surface appearance of any dark and mysterious object can be very deceiving.
So these two spheres, as far as I can tell, have exactly the same mass, the same compressibility, the same color. If I were a spacecraft orbiting these, and these were asteroids, I'd be very hard-pressed to tell which was which. Yet, if I dropped them from a height, and only one of them bounces, really illustrates the fact that one of these responds elastically, and one of these responds like a lump of clay. And it's critical to really go and find out what's inside before we even start thinking about moving these things around.
When a 3D model of the asteroid Castellia got smacked in a computer simulation, a problem occurred. An impact with the same energy as the Hiroshima bomb turned Castellia into a pile of rubble, but did not deflect its trajectory in any significant way. But there are other ways to apply force to deflecting an incoming asteroid. Using the power of the sun to push dangerous rocks out of the way may not be so far-fetched after all.
This is a typical near-Earth asteroid. Its name is Galevka. It's about half a kilometer across. It's a hazardous asteroid. Its most likely fate is going to be to strike the Earth someday, thousands of years from now.
Modern-day researchers like Eric Asfaug say the idea of a giant orbital magnifying glass to burn space rocks could work.
You create a vapor plume in one direction, and that starts the asteroid moving in the other. It's a very gradual process. It's not going to happen instantaneously. You need to know where this guy is 100 years or 50 years ahead of time. But if you do, you've got all the time in the world for a satellite to sit there, no human intervention whatsoever, and it'll gradually shove the asteroid into a different orbit, and it'll miss the Earth.
Some of the technology to do this already exists. Take an inflatable parabolic antenna the size of a tennis court, convert it to a solar collector, and use it to focus sunlight on an asteroid. The Russians have built and are testing a giant sail that captures the minute pressure of sunlight. Just attach the sail to an asteroid and let the rock hitch a ride to someplace else. But using the sun to save the Earth means waiting for nature to do the work. If we don't see an asteroid until the last minute, solar power would be too little, too late. A nuclear electric plasma engine could push an asteroid out of harm's way. The rocket technology at this NASA lab in Houston, Texas, could provide the power for a space tugboat. A group of astronauts and aerospace engineers is designing the B612 mission to prove that asteroid deflection can be done with existing technology.
These are rockets that have very tiny amounts of thrust, but they are so frugal in the use of propellant that we can keep the rocket going for periods of the orders of a year.
Building a better rocket engine is only the first step. Figuring out how to latch on to an asteroid, point it in the right direction, and push without losing control is the really tricky part. After years of research, NASA finally had it, the first complete draft of a plan, a demonstration mission, to save the planet.
We can move the asteroid off the impact with the Earth 10 years later so that it misses the Earth, and not just miss it randomly, but miss it very precisely so that we don't simply pass on the problem to our grandchildren.
Midway through 2003, the Space Guard survey had reached the halfway point. A little more than half of the kilometer-sized near-Earth asteroids had been located, and the news was mostly good.
For the 60% that we have already found, I can tell you that there is not a single one that poses a danger. For the 40% that we have not yet found, I can tell you nothing. One could hit tomorrow. Not very likely, but until we've found them and cataloged them, we won't know.
But finding the really big asteroids, those 1 kilometer monster rocks capable of ending human civilization, is only the first part of the challenge. There are an estimated 50,000 smaller asteroids that are big enough to cause tidal waves or destroy vast regions of the Earth.
A 200-meter asteroid happens maybe once every 10,000 years, but that's like 600 megatons to 800 megatons exploding in one place.
Recall the small 60-meter rock that exploded over Siberia in 1908? Well, even though it could have destroyed a city like London or New York, rocks that small are not included in the current Space Guard survey, meaning no one is officially looking for them.
Which, of course, is the same thing as saying that chances are enormous that a Tunguska-sized object will find us before we even see it coming, as happened in 1908. That is likely to happen nowadays, that we won't see it coming.
There has been talk of expanding the search to include smaller asteroids. It'll take more and bigger telescopes and, of course, more money. But until we do, we'll have no idea where those city-killer rocks are.
Evolution on Earth has proceeded in part because every so often a global catastrophe comes along, pushes the reset button, and new things happen.
It wiped out the dinosaurs 65 million years ago, and at the time, we mammals were just furry little creatures burrowing around in the ground, and an asteroid or a comet impact took out our principal competition.
I guess we are saying implicitly, if not explicitly, that we want to do away with that natural cycle.
We've had enough evolution. We like ourselves on the top of the ladder. And we can do something which will change cosmic evolution from this point forward in terms of life on Earth.
Dinosaurs ruled the Earth until a big rock wiped them out. The question is, will another rock do the same to humanity?
Let's get a couple good pictures here.
Humans are the first species with the potential to block a doomsday rock and switch off the evolutionary reset button.
People very often say, look, you're just a doomsayer. You think that these awful things are going to happen. I'm not that way at all. I'm entirely optimistic. The way in which I view asteroids and comets and the possibility of them hitting the Earth is that it's a great challenge. Thank goodness we've realized the hazard and the danger before the next one happens. It's given us time, we hope, to do something about it.
Scientists can study the sky and find the dangerous rocks ahead of time. Astronomers can do the math and predict the orbits. People have the desire and the right stuff to do the job. There's a whole new field of science that could give humanity an option the dinosaurs never had.
To the broiling heat of Earth's closest neighbor, radical weather is the norm in the solar system. We do have our own extremes here on Earth, but they pale in comparison to the fastest, dustiest, wettest, and most brutal alien storms. On Earth, the sun drives our weather, and sometimes drives it wild. When hot and cold collide in the atmosphere, watch out. This is true locally and globally. But storms on other planets are bigger, badder, and stranger than their counterparts on Earth. Why is that? Because of the sun? If not, what else fuels their fury? The basic laws of nature, the rules of the game, are pretty much the same wherever you go in the solar system. But every planet has its own way of playing the game. Right now on Mars, the entire planet is being covered in dust. This global dust storm blocks 99% of the sun's rays from reaching the planet's surface. It's actually a system of smaller but still massive storms churning dust high into the atmosphere. Once it starts, it takes months for Martian skies to clear.
Mars is just the most dramatic weather in the solar system in some senses. It's very rare in the solar system you get a weather event that can take out the whole planet.
So if the basic rules of hot and cold are the same on Mars, why is the weather so different from Earth? For one thing, Mars is half the size of Earth. It's also 50% further from the sun, so it's much colder. The average temperature on Mars is minus 80 degrees. That's almost 130 degrees colder than Earth. And the atmosphere is extremely thin and composed mostly of carbon dioxide. But perhaps the most important difference is this: Mars is a global desert.
What would Earth be like without water? Well, it'd probably have a lot of dust.
There's no liquid water at the surface of Mars, and there's very little water in the atmosphere, and so there's nothing to sort of keep the dust down.
On Earth, dust storms are localized and short-lived.
The reason for that difference in scale is that the storms are generating their own weather on Mars, whereas on the Earth, they're slave to the weather that's going on around them.
In other words, on Earth, the global weather system creates dust storms. On Mars, the storms create a global weather system. Astronomers have always been able to see big Martian dust storms easily with Earth-based telescopes. But what they couldn't see was what caused them. That would require a trip to Mars itself. In 2003, NASA landed 2 rovers called Spirit and Opportunity on the Martian surface. Their mission? To learn more about the geology of the red planet. NASA engineers always assumed that as these 2 vehicles roamed the Martian surface, dust would build up on their solar panels.
If you have a lot of dust that's falling down out of the atmosphere and coating the panels, pretty soon you're not getting much sun to the silicon. And in fact, we thought that that was what was going to kill the rover Spirit and Opportunity.
Only it never happened. The rovers didn't die as expected. As dust built up on the panels, somehow something would clean them off. But how could this be? NASA engineers were baffled until the rovers themselves saw the culprit. Martian dust devils.
It turns out that dust devils were sort of our white knight. They came along and cleaned off the solar panels just at the time we were expecting to start having some problems.
There are beautiful photos that actually show dust devils moving across the Martian atmosphere and ghostly soldiers moving out there in the distance.
A dust devil is really an extreme form of rising hot air or convection.
And that hot air wants to go up, and it comes up just like, water going down a drain. Well, this is air that just spirals up into the colder parts of the atmosphere.
Whenever warmer air, which is less dense, rises up through cooler air, which is more dense, it rotates as it swirls upwards. Convection can be very powerful, strong enough to lift things up. On Earth, it lifts moisture, and that's how thunderstorms form. But on Mars, there is no moisture, so it lifts dry, dark dust and creates giant dust storms instead. Once airborne, Martian dust clouds absorb sunlight and heat the atmosphere. This supercharges the convection, lifting still more dust.
That produces more winds, which bring up more dust, and these things can spread up to thousands of miles across, or even, in some cases, they can envelop the entire planet.
And because the Martian atmosphere is so thin, it doesn't take much to get this cycle going.
You get a lot more difference between the surface temperature and the air temperature, and so the convection on Mars is very much more vigorous.
As a rule, Earth doesn't get the temperature extremes that Mars does. But sometimes, here and there in the deserts of Earth, convection can be very Martian-like. And we get dust devils, too. But at Arizona State University, Lynn Necrace makes dust devils to order in a lab to study them up close. He uses a vortex generator and substitutes lighter, dry ice for dust. What he creates is not an exact replica of how real dust devils form, but good enough to see how they pick up dust and debris.
Natural dust devils usually form from the bottom up, as opposed to tornadoes, which form from top down. So what happens when we turn this on, we have the airflow starting, and as the airflow starts to rotate from the fans down to the floor, we actually end up having the vortex form.
In other words, the vortex generator, basically a huge vacuum cleaner, imitates the swirling action of convection.
You can see here there's a wider base where larger particles of the dry ice are being swept up, and it gets wrapped up and tightens as it expands upward. The center of the core is where the majority of the lifting would occur.
Martian dust devils have been helpful, keeping the rovers clean. But could they actually be making a mess of the rest of the planet? Some scientists think there are so many at any one time, and they lift so much dust into the atmosphere, that together they trigger these much larger dust storms.
It starts wind patterns, and the air's warmer over here, and it's colder over here, and the air starts moving around. Pretty soon you're spreading dust over the whole planet.
And we found measurements that indicate there's up to maybe 200 dust devils per square mile per day during some parts of the summer.
And they can range from a couple of 100 feet tall to devils that stretch 6 or 7 miles high.
You can get just towering monsters of dust devils that we would never see on the Earth. The kind of maximum size dust devils you see on Mars are more like tornadoes on the Earth, where they're going up almost 10 kilometers. So these things are just real monster systems.
Back at Arizona State University, scientists blow crushed walnut shells as silicate particles in the Planetary Geology Wind Tunnel to replicate dust and wind conditions on Mars.
If we can understand and sort of replicate what's going on, then we can, in a sense, understand how the Martian surface has been changing and continues to change as time goes on.
Oddly enough, their studies reveal that it's easier for winds to loft larger sand particles into the air than smaller dust particles.
This is because there's cohesional forces and static forces between the very small, fine dust grains. We imaged the rover deck and actually found that sand seemed to have bounced onto the solar panels, and we can see the skip marks across the surface. Now, this is interesting because we don't usually see sand typically reach that high.
Dust devils on Earth never have the punch to produce that kind of chaos here. Lucky for us. But what would happen to Earth if a giant Martian-style dust storm did overtake us?
If you had dust storms of Martian size on the Earth, you would find your city being enveloped in an orange-tan haze.
Air quality plunges as the storm churns. Dust blots out the sun, shutting down photosynthesis. No plants, no food. Temperatures would plummet. 65 million years ago, an asteroid may have struck the Earth, creating these same conditions, wiping out the dinosaurs.
It's not going to happen on the Earth, though, because there's going to be rainfall and moisture condensing on the dust grains and so forth and dropping them out of the atmosphere. So it's very hard for something like that to spread in the climate conditions that we have on Earth.
Forecasting Martian weather may someday be just as important as forecasting the weather on Earth. If we ever want to send a manned mission there,
the word environment no longer really applies just to the meadow next door and the little stream down at the end of town. It's the whole inner solar system. I mean, that's really our environment now.
The sun's energy bathes all the planets. On Earth, it creates hurricanes. On Mars, planet-wide dust storms. But with almost no solar energy, distant Neptune produces violent and powerful winds. Where do they come from? And just how bad are they? If Neptune's winds were to travel to Earth, these alien storms would literally blow us away. The orbit of Neptune lies 3 billion miles from the Sun, at the outer edge of the solar system. There's a lot we don't know about this big blue planet. Neptune's jet stream winds blast as fast as 1,500 miles an hour in its upper atmosphere. But how? The sun controls the weather on Earth and Mars, but it barely reaches out here. No sunlight means freezing temperatures, an average of minus 392 degrees Fahrenheit. So if there's no sun and no heat, where do these incredible winds come from?
One of the interesting puzzles is that as you go further out in the solar system, you get further from the sun, the winds don't go down. You still get very strong winds.
The energy for Neptune's winds must come from somewhere, and scientists are working to figure it out.
Neptune's energy is certainly not going to be powered by solar radiation. In fact, the energy we detect coming out from the planet in the infrared as heat is 2.5 times the energy coming in from the sun.
So the planet is creating its own heat, not from its core, which is made of rock and ice, but wrapped around this icy center is a mantle of ammonia, methane, and water, all being squeezed by enormous pressure and generating tons of heat. So while Neptune is frigid on the outside, on the inside it's giving off a lot of heat. This heat may help generate Neptune's winds, but they're still too strong to come from the mantle alone. something else is pushing them faster and faster. Earth has a hot core too, and it's a lot closer to the sun. So why don't we have winds like Neptune? For one thing, our oceans store and release energy, and that helps generate our weather.
It adds energy in places, takes it out in others, in a very complicated system.
This complicated system produces a lot of wind. And just where are Earth's fastest winds found? Surprisingly, not over the ocean. They blow instead over the top of a fairly modestly sized mountain. New Hampshire's Mount Washington.
The highest winds ever observed by human beings were right here on Mount Washington at 231 miles an hour on April 12th in 1934.
Mount Washington Observatory, a private, non-profit scientific institution, is responsible for tracking the weather and climate atop the 6,288-foot-tall mountain. This remote weather station, accessible only by snow tractor in the winter, has kept daily records for the last 76 years.
It's definitely one of the most extreme locations on the planet. We regularly see in the wintertime winds exceeding 100 miles per hour every few days.
Nowhere near as ferocious as Neptune, yet still pretty strong. But why does this mountain, 1/5 the size of Everest, produce such fierce gusts?
We're at a place where we have winds converging from various directions, coming from the Ohio River Valley, coming down from the St. Lawrence River Valley, coming up the eastern seaboard, all converging here in this area on top of Mount Washington.
The elevation change from the valley floor to the summit of Mount Washington is very significant for any mountain range. It's over 4,000 feet, so air is forced to go over the mountaintop and forced to squeeze in there, and is accelerated as it's squeezed over the mountaintop.
And they measure it every hour, on the hour, 24 hours a day, 7 days a week.
It's blowing over 100 out here right now. Ice is forming on the instruments more quickly. Time to go up and de-ice the instruments, even though it's blowing over 100. We got to do it every hour now.
Ironically, Earth's uneven surface, which channels winds into powerful gusts on Mount Washington, ultimately knocks them down over time. And this is the big difference between weather on Earth and weather on Neptune. Earth has mountains that slow winds down. Neptune is as smooth as a cue ball.
It's not so much a question of you're driving them stronger, because you're not. It's just that there's nothing to slow them down.
Simply put, once Neptune's winds get blowing, there's nothing to get in their way. So what would an average Neptune wind speed of 850 miles an hour do to us here on Earth?
We have parking level winds in the Earth sometimes above 100 miles an hour. We consider that pretty dangerous. So if we sat with 900 mile an hour winds from Neptune on the Earth, we would probably start wiping out everything on the surface and scraping everything off.
Giant Neptune takes wind and transforms it into something extreme and almost unrecognizable. But orbiting just beyond the rings of Saturn is a small moon that does the same thing to rain. This is Titan, where an everyday rain shower would turn Earth into an explosive fireball. It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn. And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface. And that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen, like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Here on Earth, our atmosphere has a huge supply of water in it all the time, constantly evaporating and raining back down, like here on the Hawaiian island of Kauai.
Today we're on the slopes of Mount Waialeale, which is the cloud-shrouded mountain behind us. It rains over 40 feet a year here.
Earth's water cycle starts when warm, moist ocean air rises, forming clouds that eventually condense into rain. The rain falls back onto the land, where it eventually drains back into the ocean, starting the cycle again.
When water evaporates, it absorbs solar radiation. When water condenses, it releases all that energy into the atmosphere. And this transfer of heat helps to moderate conditions on Earth.
Earth's water stores as much as 80% of the sun's heat, helping keep our temperatures steady from the equator to the poles. Scientists theorize that Titan might have water or some other liquid that might produce a similar effect. And in 2004, when NASA's Cassini probe visited Saturn, it found some pretty good evidence to support that idea.
If you went to Titan and you were looking at the landscape, you would see something that in some ways would look almost familiar to you. You might see big mountains and valleys that were carved out by running liquids.
In fact, as Cassini flew past hazy Titan, its radar read the surface below. Scientists saw channels cutting across the surface, much like rivers on Earth do. Some as long as 900 miles. The first strong evidence of liquid on Titan.
There are large bodies of liquid on the surface of Titan. Nowhere else in the solar system except for the Earth are there any large bodies of liquid.
Could water, the liquid that carves Earth's mountains and valleys, also be carving these features on Titan's surface? Or could it be something else? The problem is that Titan is too far away from the sun. If it was water, it would be frozen solid.
It's about -300 Fahrenheit on Titan, so things behave very differently on Titan than on Earth. Because it's so cold, methane, which is a gas on Earth, is a liquid on Titan.
One mystery solved. But just because methane is a liquid on Titan's surface doesn't mean it's part of a weather cycle like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery, literally.
Titan is completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, the Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons, so we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface, on a lake for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere that's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it, and so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the great red spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great Red Spot.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes. Also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy, and they rotate. But there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone, and that's a region of very calm winds and no clouds, and usually has a size of about 10-20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans, and the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing, plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the Pacific rather than in Los Angeles. So it's like if the trajectory was deflected to its right. And that's what we call the Coriolis force.
This force spins storms clockwise in our southern hemisphere. But there is a stark difference between Earth and Jupiter. The Great Red Spot is in Jupiter's southern hemisphere, and yet it spins counterclockwise. This is because of some other powerful winds.
It's bounded by jets, which are moving in opposite directions. And so like a cog between two conveyor belts, they're just feeding energy and momentum into the system.
Jupiter's complex jet streams spin the storm into organized chaos. But the greatest difference between Jupiter's red spot and our storms may be Earth's solid surface. Once a hurricane hits land, it comes apart pretty fast.
Where they come over land or over mountains, their behavior is very different from where they form over the oceans, and over warm oceans in particular, where we get hurricanes. And on Jupiter, there's obviously no solid surface.
With no land mass to stop it, the Great Red Spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the Great Red Spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go up to Category 5 hurricanes, nothing but Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. Something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't impede the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide, giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit, not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you probably start getting some smoldering smoke, and way before it gets to 900 degrees, the Earth would burst into flames because of all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find a planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn. lightning cuts the sky. This violent weather system grows bigger than the entire United States as it pummels the atmosphere with the most powerful lightning ever seen. Except this lightning can't be seen, because these bolts are electrifying the skies over Saturn. Despite the raw power of Saturn's lightning, scientists have been unable to see it, partly because Saturn's rings are too bright.
The rings are so bright, if you were on the night side of Saturn, it would be considerably brighter than the Earth under a full moon.
But Saturn also hides its lightning within thick, choking clouds of ammonia.
It's probably 100 kilometers down that the lightning is happening, and that complicates seeing the lightning flashes.
But the lightning is there, and scientists know it because they've heard it. Radio wave detectors on the Cassini orbiter have recorded the sound of Saturn's lightning.
We can hear the static of lightning just as you could with an AM radio going down the highway on Earth.
And this static reveals the power of the lightning that we can't see.
You can measure the energy in those radio waves and compare it with the energy that your radio picks up when there's a thunderstorm around on Earth. And the Saturn ones are big. They're more powerful, maybe 100 times.
And Earth's lightning can help scientists understand how storms work on Saturn. Within Earth's storm clouds, just like in Saturn's, updrafts drive moisture higher, causing ice to form. These ice crystals rub against each other, take on a positive charge, and become attracted to negatively charged water droplets lower in the cloud. This sets the stage for a potentially powerful discharge of energy.
Once you get that charge separation that builds up so intensely that some theorize that it can be as strong as 100 million volts, that the cloud then must release that energy.
On Saturn, the same thing happens on a much larger scale. In fact, the lightning is 100 times stronger than Earth's. That's a staggering 10 billion volts of electricity. Thunderstorms in Saturn's southern hemisphere span thousands of miles and can last as long as a month. But scientists aren't sure what makes Saturn's storms bigger and longer lasting. It could be Saturn's supersaturated atmosphere.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storms bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you'll see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart, and it allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.
It was hoped that lunar rocks would help solve that mystery. The Apollo 11 mission in 1969 marked the beginning of direct human exploration on the moon. During 6 missions, 382 kilograms of lunar rock were collected. Transporting all that from far-flung locations on the moon's surface required a lot of power. Apollo 15 finally developed the answer: the Lunar Roving Vehicle. Moving about freely on the moon's surface, this lunar rover could take astronauts farther afield than they could go on foot. However, developing the rover was very much a matter of trial and error. The lunar soil would be very different from Earth's. Engineers had to develop a vehicle that could operate on all kinds of terrain. Weighing just 200 kilograms, but capable of carrying a 500-kilogram load. A supercar that would be used to locate and transport rocks on the surface of the moon.
It was a great vehicle. They did a wonderful job in building it, you know, especially for those days. It's hard to believe now. We're talking how long ago? 40 years, 30 years? What are we talking, you know?
The last flight in the Apollo program was Apollo 17. On this mission, NASA finally included a scientist astronaut. This was a final chance to investigate on the moon's surface, a gamble that they could discover lunar materials of types never found before.
Hey, there is orange soil. Orange!
They succeeded far beyond their expectations, finding traces of the moon's dramatically violent past. This is the story of how the Apollo program developed a vehicle that could drive around on the moon, collecting rocks and soil that revealed billions of years of history. From time immemorial, people have cast longing glances at the moon and wished for a chance to travel there. The first person to make that dream come true was the brilliant rocket scientist Wernher von Braun. He led the Apollo program, which actually landed men on the moon. A decade before the start of the Apollo program, von Braun's conceptualizations of space development were carried in a magazine. At a time when it wasn't even known if humans could traverse the distance to the moon and back, his blueprints for space development were bold and detailed. Each and every conceptual drawing overflowed with von Braun's enthusiasm for space travel. Exploration on the moon's surface was also included. A major role was to be played by lunar rovers. They were to function somewhat like the covered wagons that blazed trails through the American West. Clearly, even before space travel began in earnest, a lunar vehicle was conceived of as essential to exploration on the moon's surface. The latter half of the 1950s saw the start of a space race between the United States and the Soviet Union. These two superpowers staked their prestige on efforts to launch artificial satellites. In 1961, the Apollo program was launched, with von Braun playing a central role. The next year, development of a lunar vehicle began. Its construction proceeded in tandem with development of the Apollo rocket engines themselves. The best regarded prospect from that phase of development has been preserved. The MoLab, or Mobile Laboratory, built in 1964. The tires were huge. The vehicle was 9 meters long and weighed 3 tons. The inside was spacious. The design permitted 2 astronauts to live and work there for 2 weeks. The steering wheel and foot pedals were the same size as in an ordinary passenger vehicle. Development was spearheaded by 2 representatives of America's largest auto manufacturer, Chief Engineer Ferenc Pavliks and team leader Samuel Romano. Development went smoothly, but this rover never made it to the moon's surface. The problem was that massive body. NASA realized that they would need another rocket just for the rover, in addition to the one carrying the astronauts. In 1966, the year before the scheduled first trip to the moon, development on the lunar rover was suspended. It was a setback, but the developers waited for another chance.
Our job is laid out for us. Our task is laid out for us, yeah. But we didn't have any problem. We didn't think that we couldn't do it. It was our job to get it done, and we got it done.
In March 1969, faced with the upcoming launch of Apollo 11, the 2 men went to inspect the completed lunar module, or landing craft. They knew that their only hope of getting a rover onto the moon would be aboard the lunar module. But the lunar module had no space to spare, except for one unused compartment they spotted. It was a recess just 1.5 meters square and 0.9 meters deep.
Well, when we first saw this is impossible. We couldn't fit this larger vehicle in that space.
But Pavliks, the engineer, did not give up. He tried to see how compact he could make the rover. To carry 2 astronauts, it had to be at least 3 meters long. To get around on the moon's rock-strewn surface, It had to have large tires. But any way they calculated it, it was too big to fit on the lunar landing module. Was there no way to get it onto the lunar module? For 3 months, they experimented with mock-ups. Then, one day,
it's usually these ideas come very suddenly, you know. Eureka.
what was this sudden inspiration? Pavliks demonstrates with a 1/6 model.
Then the seats must be folded down. Then the front chassis, which is hinged, is folded over 180 degrees. Then the same way, the rear chassis is folded up. Then the wheels are folded in to the 45-degree angle. And then the complete assembly fits into that triangular shaped envelope, which is between two legs of the lunar landing module.
It was ingenious. A foldable vehicle was a huge step toward including a rover in the moon landing mission. 2 weeks before the scheduled launch of Apollo 11, the two men took their model to NASA for a demonstration.
When we went to Huntsville, and the engineering people were very excited that, hey, maybe this could work, okay? So one of the engineers said, why don't we show it to Dr. von Braun, who was the director of the Huntsville NASA organization.
Von Braun had the final say on lunar rover development. They had to arouse his interest and enthusiasm. Pavliks had an idea how to do that.
So he led the way to von Braun's office, opened the door, and I guided the vehicle into his office with radio control, that he couldn't see anybody but this little vehicle coming into his office. And he was on the telephone, saw this little thing coming in, and put the telephone down and said, what is this? And then we walked into the office, explained to him what the concept is, demonstrated all the folding up.
Von Braun listened intently. Then, suddenly,
he slammed his hand on the table and he said, we must do this. We must run a vehicle on the moon. And we convinced NASA to go ahead and do it, and we got a contract to do it.
The lunar rover concept championed by the two men had previously been scuttled. Now they'd been given a second chance. Two weeks later, Apollo 11 was launched. The entire world awaited the moon landing with bated breath. The rehearsals for the Apollo program of putting men on the moon and bringing them back were over. This was the real thing. Three months later, the lunar rover project began in earnest. It had a new and powerful supporter, Saverio Morea. Morea was a capable manager who had overseen the successful development of the Apollo program's giant rocket engines.
All they do to send out the next model car, it takes them like 4 years before they're happy with the design and they can finally put one out on the street. That's different. We had to produce flight hardware for astronauts in a totally unknown environment in 17.5 months.
Starting with Apollo 11, NASA was planning on about one moon landing every 6 months. Apollo 15 was scheduled to undertake full-scale research on the moon's surface in 1971, just 2 years away. The lunar rover would have to be operational for that mission. The contract required development and production within a mere 18 months. This vehicle would be the first ever to run on a surface other than planet Earth's. It was a tough schedule, but they started development by trial and error. The first requirement was the capability to roam freely over the moon's rough terrain. The lunar rover would be useless unless it could easily surmount obstacles as high as 30 centimeters. The vehicle utilized technologies that were still unavailable to vehicles on Earth. It was an electric car whose 4 wheels were powered by dedicated motors drawing on 2 silver zinc batteries. The 4 motors put out a combined total of 1 horsepower. That was enough for the moon, whose gravity is only 1/6 that of Earth's. Operation was simplified. The manual controller had steering, acceleration, and braking functions all there at the driver's fingertips. Later, to accommodate the bulkiness of the astronaut spacesuits, the controller was reconfigured to a T-shape, so the driver's hand could rest on it comfortably. The design goal was operational ease. Maneuvering the rover was simple. Tilt the controller forward to start moving. Tilt right, it turns right. Tilt left, it turns left. Pull back to engage the brake. Push the button and pull back to put it in reverse. In test runs, actual astronauts checked out every feature very carefully. It functioned superbly. Everyone agreed development had gone well. Morea, however, spotted a surprising flaw.
Not so much the vehicle itself, but how the man would interact with a vehicle like ours in a 1/6G environment.
But what would it be like on the surface of the moon? No one could predict that. So they tested the rover's seats inside a large airplane, which was flown so as to simulate 1/6 of the Earth's gravity. This is the footage of that experiment. The astronaut flops about and can't get seated. There was no point in having a rover one could not ride. But this problem was solved with a little ingenuity. A 15-centimeter bolt protruding from the floor of the car body. The astronaut could then hook his foot briefly under the bolt, levering himself onto and into the seat. Problem solved.
That was the big one. Simple solution, but big issue. This was not simplistic. This was a spacecraft on wheels.
April 1970. By now, they had reached Apollo 13, but the lunar rover had run into a seemingly impassable developmental wall. The problem? The material and shape of those huge tires. In the vacuum of space, pneumatic rubber tires would blow out. They were simply not practical. What's more, on the moon, the terrain, scarred from the impact of countless small meteorites, is uneven, full of potholes. But in some places, the soil is finely granulated, like powder. The tires would have to do well on that sort of terrain as well. They needed something strong, resistant to temperature fluctuations. They thought of a material quite unsuitable for terrestrial tires: metal.
Should be flexible because it was carrying people, so the ride characteristic had to be such that it cannot be a rigid wheel. So we came up with this idea of making a flexible wheel, making it out of spring material.
So they created 10 types of metal wheels or tires and tested each and every type. It had to be lightweight and suited to any terrain. It also had to give a comfortable ride. This is the one they finally chose. Metal filaments were woven together at 4-millimeter intervals. This was a wire mesh tire.
This wheel is a very good simulation of an actual tire. It yields as you press on it, and it returns, and it has enough strength to carry the weight of the vehicle. So it seemed like it, and it can't blow out.
Romano's team had overcome their greatest obstacle. Where does a wire mesh tire get its strength and versatility? Kazuya Yoshida, who helped develop the Japanese asteroid explorer Hayabusa, ran some tests. He fabricated two 15-centimeter diameter wire mesh tires and attached them to a small testing unit. A rock was inserted in the test bed to create a 3-centimeter high obstacle. How will the tires perform? The test unit easily negotiates the obstacle. When tire meets rock, the tire changes shape to accommodate the rock. That suppleness in the wire mesh tire, allowing it to traverse both rocky ground and softer soil, is exactly what is needed on variable terrain like the moon's. The rover was now outfitted with wire mesh tires. The next step was to simulate lunar conditions for full-scale testing. One trick was to have the rover lifted slightly by a crane as it ran. so it would be 1/6 of its real weight, as it would be on the Moon. Only after it passed numerous performance tests was the lunar rover deemed ready. Just 4 months before the scheduled flight of Apollo 15, the lunar rover was packed into the side of the landing module. And NASA was setting a new plan in motion. The Moon's surface has both dark-colored and light-colored areas. Up to Apollo 14, the Moon landings had all been on the dark areas. They are called seas, and they are flat. That made them relatively safe for landing. But the only kind of rock they could find in such places was basalt. There's plenty of that on Earth. So Apollo 15 would approach one of the light areas instead. The plan was to set the lunar module down near the edge of a dark sea, and then have astronauts set out in the rover for brighter, higher ground. NASA had not yet obtained any rocks from the Moon's highlands. July 26, 1971. With the lunar rover on board for the very first time, Apollo 15 took off for the Moon. Taking the rover made this an historic flight, one that marked the beginning of true lunar exploration. Four days later, the Falcon lunar landing module set down safely on one of the Moon's seas, near a mountain range. They were about to realize the fruits of a year and a half of development. An astronaut held the rope that would release the lunar rover from its cargo bay. Back at Mission Control, the two men who had worked so hard to develop the rover held their breath. The rope is yanked hard, and the rover begins to emerge. All it took was one quick pull for the rover to start to deploy. In just 5 minutes, there was the lunar rover, ready to roll. But then came something unforeseen.
Okay. Got a deep hit. We're moving. Extraordinary. Negative. But I don't have any front steering, Joe.
There was no front steering at all.
Oops, yeah, it was oops. As a matter of fact, within minutes, I got a call from the vice president from Detroit, General Motors, that what's going on? Can you fix the problem? So it was a high, visibility type of operation.
No front steering could have been a serious setback. But the rover had a built-in feature that saved the day. The front and rear wheels actually operated in tandem in a four-wheel steering system. To turn right, for example, the front wheels would point right and the rear wheels would point left, all four contributing to the turn. On Apollo 15, the front wheels did not steer when first powered up, but the independently powered back wheels still operated sufficiently for the vehicle to be maneuvered. "40 minutes later, the rover was declared ready to explore the moon.
Man, this is really a rock and rollin' ride, isn't it? Never been on a ride like this before. Boy, oh boy. I'm glad they got this great suspension system on this thing. Boy.
Average speed, 12 kilometers per hour. The two astronauts riding the rover were just ecstatic. Then, suddenly, they realized they could no longer see the lunar module. Since the moon is only 1/4 the size of Earth, traveling 3 kilometers as they had put them beyond the horizon. But that was no cause for alarm. They had built-in technology that gave them distance and angle to the lunar module. The first ever lunar car navigation system. With no fear of getting lost, they were emboldened to go even beyond the sight lines to the lunar module. On the second day of exploration, they made a great discovery. It was while the rover was en route to higher ground. The two explorers were at the edge of a vast crater.
Okay, Jimmy, let's go to work. Roger. Look at that. Almost see twinning in there. Guess what we just found? I think we found what we came for. Crystal and rock, huh? Yes, sir. You better believe it.
It was a white rock, which they called the Genesis Rock. The highlands were composed of rock that formed shortly after the moon itself was born. Hitherto, the lunar seas had yielded only black basalt. What Apollo 15 retrieved from the highlands was a white rock called anorthosite. This discovery made it possible to construct a scenario explaining how the moon achieved its current shape and characteristics. 4.6 billion years ago, the solar system had only just taken shape. Right after the Earth itself was born, a body the size of Mars collided with it. This giant impact, as it's called, blew a vast cloud of debris out into space. The fragments were gravitationally attracted to each other and fused in a repeated process. The result was the moon. As it took final shape, the moon was covered in magma, molten rock heated by the energy from all those collisions. In time, as the moon cooled, white anorthosite began to crystallize in the interior. With a relatively low specific gravity, the anorthosite gradually moved to the surface, where it formed the Moon's crust. So at one point, it is thought the Moon was entirely white. Then, however, the solar system was struck by a vast swarm of meteoroids. Impacts on the Moon created giant craters. They punctured the crust, through which magma pushed up from the Moon's core onto the surface. The magma, now lava, cooled in the form of black basalt. This is how the Moon's seas were formed. This account of the formation of the Moon is based on discoveries made possible by the lunar rover. In April 1972, Apollo 16 was launched. On this mission, too, the rover played a major role. It scampered easily over the Moon's rough terrain. And it covered a total of 27 kilometers, 10 times farther than an astronaut could have walked in the same time period. The lunar rover had proved to be indispensable to the Apollo program's moon-based exploration. Suddenly, it was the last Apollo mission. NASA hoped for a spectacular new discovery. The objective was a gorge, cut into steep mountains. This terrain was far more complicated than any attempted before. There was a good chance some strange new rocks would be discovered. And it was their last chance. So on Apollo 17, NASA sent in a ringer. For the first time, a scientist was aboard. A geologist named Harrison Schmitt. Nowadays, more astronauts than ever before have professional backgrounds in science and engineering. Their expertise is valued for conducting experiments in space. But on the Apollo program, given the extraordinarily complex operational requirements, all the astronauts except for Schmitt were military pilots. Schmitt had been fascinated by space since childhood, but he became a geologist. His chance to venture into space came when he was 29 years old.
It was on very short notice. The NASA and the National Academy of Sciences asked for volunteers for scientists to become astronauts in November of 1964. And I thought for about 10 seconds and decided that I would regret not volunteering, and so I volunteered.
Schmitt had never piloted anything more complex than an automobile, but NASA drummed new operational skills into him. Apollo 17 was the last chance to discover new moon rocks. Capitalizing on that chance was up to Schmitt. December 7, 1972. With one lunar rover and one scientist on board, this was Apollo's last chance. Schmidt was given the responsibility of piloting the lunar landing module. Four days later, they had reached lunar orbit. The lunar module separated from the command module and began its descent to the surface. Carefully, they descended to a narrow gap between steep mountain ridges. In the end, Schmidt and his crewmates made a successful landing.
Stand by for touchdown. Stand by.
They had landed perfectly in the middle of the valley. Surrounded by this magnificent scenery, the normally calm Schmidt could not conceal his excitement.
To all those who made it possible.
Really would be great to go to this valley, this deep mountain valley. It's deeper than the Grand Canyon of the Colorado. I mean, it was a very deep valley. It was splitting the ring of mountains around this large basin called Serenitatis. And it had these young volcanics. It had a lot of a very attractive things.
Schmidt and another astronaut boarded the rover right away and set off to investigate. They traveled west to a point 3.5 kilometers from the lunar module. Right in front of them was a crater more than 100 meters in diameter. Schmidt's instincts as a geologist told him to focus his attention on this crater.
And I think everybody in Mission Control was excited about it too, because it was so unexpected.
The geologists in Mission Control could not conceal their enthusiasm either. Until then, there had been no indication that there had ever been volcanic activity on the moon. A close look at the sand reveals tiny globs of glass, 0.1 millimeters across. They called it orange glass.
It was a volcanic deposit, what we call a pyroclastic deposit. Certainly people in Japan are very familiar with volcanoes that erupt and throw glass and debris around. Well, this had happened on the moon.
The orange glass was created 3.6 billion years ago. At the bottom of a crater made by a meteorite impact, magma spewed forth from the moon's core. A fire fountain sprayed droplets of magma from 400 kilometers below the crust out into the cold of space, where they instantly cooled into globules of glass. Schmidt and his colleagues had discovered irrefutable evidence of volcanic activity on the moon. "36 years later, the Japanese unmanned lunar explorer Kaguya photographed the moon's surface with a special camera. It identified more than 40 locations on the moon where there was sand with the same composition as the orange glass. This confirmed that the moon, like Earth, had seen a great deal of volcanic activity.
We were told later on that without the rover, NASA or the government would have cancelled the last 3 or at least 2 Apollo flights. So it was, in a sense, the rovers were saved the last 3 of the Apollo flights. because it was a new element in the exploration.
The riddle of the moon's origin was solved by the Genesis rock and orange glass, and it was the lunar rover that led to these discoveries. It's been 40 years since the end of the Apollo program. But research is still being done on the rocks brought back from the moon. New facts are even now coming to light. Alberto Saal is an associate professor of geological sciences at Brown University in the U.S. He's using Earth's latest technology to study the moon's orange glass. When the magma spewed out of those lunar craters, it instantly formed glass globules that incorporated substances from the moon's core. That makes them time capsules of the very origin of the moon. Analysis yielded unanticipated results. Trapped in the orange glass were some of the same gases that exist on Earth, such as fluorine and chlorine. This supported the theory that the moon came from the Earth. Another completely unanticipated substance was found: water. This was the first ever proof that there was water on the moon. When Earth suffered the giant impact that gave birth to the moon, the fragments of Earth dislodged into space were heated to 4,000 degrees Celsius. It had been thought that all the water would have evaporated. But where had the moon's water come from? Currently, the world's only isotope microscope is being used to analyze the moon rocks to solve that very riddle. Hisayoshi Yurimoto has been conducting research of this sort, including analysis of the Apollo mission's moon rocks. That includes measurements of deuterium, a hydrogen isotope. Amounts differ depending on the type of space object in which they are found. The water in the moon rocks contains from 0.02 to 0.03% deuterium. Comparable amounts of deuterium are found in another well-known type of space object: comets. In the solar system of 4 billion years ago, there were many more comets than there are now passing through. Yurimoto believes that the moon was showered with a huge quantity of comet ice in that era, when the comets passed too close to the sun. At that time, it recouped some of the water lost after the event of the giant impact. Since the Apollo missions, no one has walked on the moon. But plans are underway now for new moonwalks. In 2009, the U.S. launched the Lunar Reconnaissance Orbiter, or LRO. It is parked in lunar orbit 21 kilometers above the moon, from which it photographs the surface. This is an effort to compile detailed information for the next people who attempt to conduct investigations on the moon's surface. This is one of the images captured by the LRO. It's the Apollo 17 lunar landing site. Those spidery lines mark where the lunar rover scudded across the moon's surface. Their tracks remain even now. At the end of one of those tracks, a lunar roving vehicle, no longer roving. The rover was a major player in moon explorations of an earlier era. Now it sits there patiently, waiting to greet new explorers from Earth.